answers because I actually do give you the test statistic. 5, assessing normality using a chi-square distribution. That thing I did last week. 6, analysis of paired data. We have paired data. And what we're going to do right now, analysis of variance. So we started out, of course, with sampling distributions, and then we did confidence intervals and tests of hypotheses about, grab a marker here, really, a lot of different things. Ooh, that's not very good. I shouldn't be using that one. P and mu and P1 minus P2 and mu1 minus mu2 and a variance and a ratio of 2 variances. I left that one off the final. I left it off. I was up to 7. I went, yeah, that's good enough. I left that off. And then also a mean difference. That's that paired data thing. Cut the data sets very small. I could have given you very large data sets and maybe gone to the computer. But I wanted to keep it manageable. Yeah. So one sample here. Okay. Technically here, one sample here. One sample and paired data from that one sample. Okay. 2 samples here. Then last week we did a chi-square, okay, with 3 or more samples. That would be a chi-square test of homogeneity. Today, analysis of variance, which compares means from 3 or more samples. And then I'm going to continue with regression, really important. If you take, Dr. D'Amico is teaching linear models, okay, and he's going to want to know darn well what you guys know. Yeah, as I said, I know him real well. We share the office together. I share his office, so I'm going to show him exactly what you guys know. And I got a real good start to finish thing on linear regression, but more about that later. Let's take a look at analysis of variance. I'm actually going to need this hope everybody's okay looking at it this way, because I'm going to be writing on it. But here's our little study. In a randomized experiment, lab mice were fed different doses of dye, red dye 40, and followed time until that. A good example, but it's an interesting one that harkens back a little to the red dye scare way before your time. I think it was the 1970s, maybe the 1980s, and food red dye was added to various foods to make it pretty. And one type of dye, I'm an expert on this story, but one type of dye was found to be hazardous to one's health. Right? So all of a sudden manufacturers are stopping the red dye. That affected M&Ms. Now, the Mars company swore up and down that we do not use red dye number whatever it was. We could not use it, but nevertheless, they pulled the red M&Ms off the shelf. Yep, no more red M&Ms for a while. And that stayed that way until I don't know, some years later, years and the whole red dye thing, everybody forgot about it. And then there was a campaign, bring back the red M&Ms, right? So yeah, that's the story on that one. So anyway, so mice are fed low, medium, and high doses of red dye 40 with a control group. And again, what we're looking at, time of death, The Greeks did the advice blast. I see 101, close to 2 years. Okay. Down below we have some summary statistics. Most important means. Okay, now there's the control group. They lasted the longest on average. Low, that's on average about 70 years, 71 years, not really big difference here, 65 years for that. Okay. We have different sample sizes. That's okay. That's all right. There's a little dot plot down here. Okay. We can see the distribution. We see some interesting things from the dot plot that weren't really very obvious from the raw data. I mean, there's the control group. That's pretty tight. That's pretty tight. Okay. There's the variation in the control group, and so about the same as the variation here, roughly. Oh, but now, with the higher dosage, data's all over the place. Data's all over the place, so there's a lot more variation, right, in medium and high groups than there are in the low and control groups, right? So, what we're going to do is produce what's called an analysis of variance table. And what this is, we're going to get to know the various pieces of the analysis of variance table. And I wanted to bring the original sheet in so I don't have to do exactly this. No problem. So first, understand what that's asking. We're going to take each value for all 4 treatments and all the mice in each treatment. We're going to take each value and subtract the grand mean. The grand mean. Right? What is the grand mean? We have the individual means, but we don't have the grand mean. I thought that I would do that for you right here and right now. So let me get into an Excel file. Okay. It's a nice way to do it. Little Excel file, and I'll paste it right there, make it a little bigger so you can see. Okay, there's the data. And all I have to do is say average. Oh, let's average all of these. Don't worry about those blanks. Excel will treat them as blanks and not 0. And the grand mean is 75. The grand mean is 75. So that first sum of squares that we were looking at, down here. Call the total sum of squares. And we're going to abbreviate that as SS total. And what we do, I'm just showing you by hand. Okay? We start with that first value of 69. And we subtract 75. We square that. And then we go to the next one, 76, right there. And we go to that one. And we subtract 75. And these, of course, are deviations from the mean. And I keep going, I keep going, I keep going until I get to the last one, 101. Yeah, I don't really feel like writing all of that. Okay. And that's called the total sum of squares. Now, you might recognize that as the numerator in a variance calculation. It's a numerator in a variance calculation. Yeah. So I got an easier way to doing it right now. I do. Okay. How many are there in total? All I have to do is add up the bottom numbers, but in total there are 38. 38. So I'm just going to take the variance of these numbers, right? Now, the variance is the sum of the squared deviations from the mean divided by, remember, n minus 1, divided by 37. So all I have to do is take that number and multiply it by 37. What is it, how do you do the mean? It's just VAR, parenthesis, from A1 to D11. B equals BAR A1 to D11, colon. Yeah. Yeah. So that number is 16,234. 16,234. That is the first of 3 numbers that I need.
How did you get that?
Well, I multiplied the variance by 37.
Maybe by
37.
dig it up here.
Yeah. Yeah. Right. Yeah. 38 ones. Yep. Okay. Now, the next one. Next one. Not going to take me too long. What did I need those sample sizes? No, here, I'll go here. We jot them down. The individual means are 90, 70, 71, 65. Other side is 11, 9, 10, and 8. Okay. The second one. What you do, for each of the 4 groups, you take the sample size, first group has 11 in it, and then you subtract the group mean from the grand mean. This one I can write out. This one is pretty easy. The next one had 9 in it, right? The group mean was 70, the grand mean is 75. The next one has 10 in it. You take the group mean of 71, subtract 75, and finally, the last one has 8 in it. Take the group mean minus the grand mean, 75, and that is, we get that. And that number is 3,660. 3,660. Okay. The last value, we're doing the same thing that we did in the first one. The same thing, except instead of always subtracting 75, the grand mean, this time you subtract the group means. This time you subtract the group means. So, all right. And this one is called the error sum of squares. Right? Oh, darn it, I just write them out. No, there they are right there. Yeah. So this last number, you start with the 69, you subtract 90 squared, go down, go until you get to the last one, subtract 90, go to the next group, 49, subtract 70, keep going until you get to the last one, subtract, might as well just keep going like this, right? That one, 30, minus the group mean of 70, keep going till you get, to the last one, 96, minus 70, and finally, 34 minus 65 squared until you get to the last one. You notice that I put them in order for no good reason. Okay. That's that calculation. These are the key numbers that we need. Now, the computer always does that for you. And that is 12,574. That's 12,574. Okay. Those are the 3 numbers. So we arrange them in a nice little table. Now, this is an Excel output. Next, I'll go through this Excel and Statlet. Okay, up here, okay, Excel gave us how many are in each group, the total, the average, and the variance. That's nice. Okay. But here we have an analysis of variance table, and that's of course what ANOVA stands for. Analysis of variance, ANOVA. Okay. So we list the sum of squares. Okay. I led off with the total sum of squares. I followed it up with what's called the between group sum of squares. And then that latter one was what we call the within group sum of squares. Yeah. Each time I'm operating within each group. Within the group 1, I'm always subtracting group mean. Within group 2, I switch over to group 2's mean. Group 3, I'm subtracting group 3's mean. And group 4, I'm subtracting group 4's mean. Okay. Whereas this one, I went between the groups. Okay. I looked at each one and how those means differed from the grand mean. And have you noticed that this plus this equals this? We call it the decomposition of the sum of squares. That we can take that total sum of squares, which again is the numerator of the variance. I mean, your variance and standard deviation are your go-to measures of variation. Well, somebody figured out that, hey, I can take that total and I can bust it up. Okay? Variance due to between group membership. Okay? Basically due to group membership. And then the random variation that occurs within each group. Okay? Degrees of freedom. Okay? Exactly what you would think. This 37 is your 38 minus 1. That's your n minus 1. The 3, there are 4 groups. So 4 minus 1. It's 4 minus 1. And this, yeah, your n is 38. And we generally denote k as the number of groups. So that 34 is the n minus k. The 37 is your traditional n minus 1, and the 3 is your k minus 1. Okay. So that's your degrees of freedom. The next column, MS, stands for mean square. Really, really, really easy, and you can see it. You can see it here. That number is this number divided by this number. If you can see it, look at the numbers. 3 divided by 3 is 1. 66 divided by 3 is 22. 0, yeah. 3660 divided by 3 is 1220. Yep. That's it. Mean square is sum of squares divided by the degrees of freedom. Boom. Right there. And finally, this F statistic is this divided by this. It's the 1220 divided by 369.8235. That is your F statistic. F statistic has an F distribution. We are familiar with that. And then you say, oh yeah, the F distribution is the one that has a pair of degree of freedom. What are they? Right here. Right there. And later on we'll get on Statlet. We'll crank one of those out. But there you go, folks. Now, once again, any Excel, Statlet, R, they'll crank out an analysis of variance table for you. I wanted to go a little bit more, give you a little bit more and tell you where those numbers come from. Yeah, I have a big problem with just shoving a table in front of your face and saying, here's how we interpret it. No. Because what a really easy example. We're able to kind of rip this apart and show you where the analysis of variance table, how it's constructed. Okay. Now, I'm going to step aside. I'm going to step away from the mice for a little. I want to give you a little more insight into this. Okay. I've got 3 follow-up examples. All right, 3 follow-up examples. Yeah. And these are contrived, more teaching examples. here's our new scenario. A manager wants to determine whether the mean times required to complete a certain task differ for 3 levels of employee training, right? He randomly selects 4 employees from each of the 3 levels of training. 3 levels are beginner, intermediate, and advanced. Do the data provide sufficient evidence to indicate that the mean times required to complete a certain task differ for at least 2 of the 3 levels of training? That's pretty much our standard question. All right, now giving you a little information here, that the grand mean is 36, and the total sum of squares, okay, your SS total, okay, is 880. All right, so let's use what we've learned to kind of simplify our work here. And I'm going to go back over here, and let's get the group means. I'm going to get the group means. All right. Group means are 45, 35, and 28. 45, 35, and 28. 45, what? 45, 35, and 28. Thanks. Okay. So, that between sum of squares. Sum of squares between, that's the easy one. We're told that the grand mean is 36. Right? So that's going to be 45 minus 36 squared. Next one, 35 minus 36 squared. Next one, 28 minus 36 squared. All right? So that is 9 squared. That's negative 1 squared. That's negative 8 squared. And I did this because I want to just point out that without the squares, 9, negative 1, negative 8, they add to 0. So this one's going to be pretty easy. 8, 81, 8, and 64. So that's 82 plus 64, and that's 146. 146. So in no time flat, I was able to get the between sum of squares. I'm going to scroll down here. Let's organize this a little bit. So I mentioned that the total sum of squares is 880. We figured out the between sum of squares, 146. All right, so I'm just assuming I did all my arithmetic correct. 7, 3, 734. That's going to be 734. Let's see, degrees of freedom. I had 3 groups of 4, 12. Right? 11, yeah. Right? My n is 12. My k is 3. Right? Number of groups minus 1, and number of observations minus the number of groups, that's 9. And yes, 11 equals 2 plus 9. So I can craft my little analysis of variance table. Yeah. Right? Just transcribing those numbers. I got the 146 here. I got the 734 here. I got the 880 here. I got my degrees of freedom, 2, 9, and 11. All right, that's pretty easy, right? That's going to be 73. I grab my calculator. I got my calculator. Yeah, calculator. 734 divided by 9. Yay. That's 81.56. All right. We don't do a total mean square. And the F statistic is 73 over 81.56. divided by 81.56. That's 0.895. 0.895. So it's a kind of smallish test statistic. That's a smallish test statistic. Yeah, because oh, yeah, you're going to see the big punchline in a minute. Here's what I'll show you. Let's get the p-value. What the heck? Where that comes from? Let's go to our favorite buddies. Okay. Tablet. Probability distribution, F distribution. And we have, let's see, 2 and 9 degrees of freedom, 2 and 9. Okay, there it is. It's always a right tail probability, always, always, always. I want the area to the right of 0.895. It's going to be pretty big. 895. Yeah, it's a lot of the area. 0.4421. All right, so the p-value is 0.442. That's fine. Okay. Perfect. Little quickie analysis of variance, right? Constructed a little table. All right. Okay. 2 more fun ones. Ooh, but quick break in the action, just because. So, users of Desmos, right? You see me use Desmos, okay? You know what I'm going to say? Anybody know what I'm going to say? Surprise, surprise. Desmos does 3D graphing now. It can do 3D graphing. By the time we're done, I'm going to show you that. OMG. I was doing some work this weekend, and I got on Desmos and said, ooh, try our new 3D feature. I went, what? Yeah. Because, it does a lot of cool stuff, 3D. Holy. I know some people on the inside of Desmos, and they say they've been working on it, but woo, it is indeed. Okay, but back to this one. Hey, here's another example. Another manager. This one selected five employees from each of the 3 levels. Okay? Now look at his results. The teaching example. Okay? Oh my gosh. First off, there is no variation within the group, right? Beginner, they all scored the same. Intermediate, they all scored the same. Advanced, they all scored the same. Any differences you see lie between the groups. Between the groups. Yes. Yeah. So this is kind of a fun one. And here I'm saying, well, the grand mean is 36. You don't even need that. The total sum of squares is 430. Okay. The total sum of squares is 430. All right? Well, the group means are, what are they? The group means are 43, 35, 43, 35, and 30. Right? So within each group, if you take each value minus the mean, you're going to get 0. There's a bunch of zeros. It's 0. There is no variation within the groups. All the variation that you see is between the groups, so that's going to be 430. Now let's see. 3 groups of 5, that's 15. Subtract 1 is 14. We still have 3 groups minus 2, so that's got to be 12. And now I can construct my ANOVA table. Okay. For this one, oh my gosh, what does it look like? Right. Now, first off, that's what you're looking for. You're looking for differences between the groups. That's your HA. I haven't introduced that yet, but that's going to be your HA. So, what was it? 440? No, 140. Yeah. What was that number?
430?
430.
Yeah.
Yeah. Wait it out there. Okay. So, the total sum of squares is 430. Right? The variance within each group is 0, which means that all of the variance is taken up between the groups. Okay, so that was 2, that was 14, and this has got to be 12. All right, so that's 215, that's 0. So technically, your F statistic is infinity. 15 divided by 0, with a p-value of 0. Okay? This is totally about the right scale. And this is what you want. So large F statistics and small p-values will support the alternative hypothesis, and the alternative hypothesis is going to say, yeah, there's a difference between the groups in terms of the mean effect. Okay? Now, that's the ridiculous extreme. That is the ridiculous extreme. But again, good teaching example. Got one more for you. Got one more for you. Okay, now, another manager, 6 of them, 6 apiece, 6 apiece. Grand mean there is 36, and this total sum of squares is 642. All right, now look at this. Look carefully. All right, I'll tell you, each group mean is the same. Each group mean is the same. There's worse than that. Okay? All 3 groups are the same. I just jumbled the numbers. 41, 41, 41, 35, 31, 45, 37, 27, yeah. The 3 groups are exactly the same. The 3 groups are. Yeah. So there is no variation between the groups, but we do see random variation within the groups. So the sum of squares, the total sum of squares is 642. 642. All right. The total sum of squares is 642. All right. But this time there's no variation, none, between the groups, because the groups are identical, and any variation we see must be within the groups, okay? Now, I changed the sample size each time just for fun. Now we got 3 groups of 6, that's 18, minus 1 is 17, still 3 groups, minus 1 is 2, so that's gonna be 15, okay? So, sum of squares, right? Total sum of squares is 642. No variation between the groups, all variation within the groups, right? 2, 15, and 17, okay? That's 0, okay? That's I don't care what. I don't care what, because when I do this divided by this, 0 divided by I don't care what, I'm going to get 0 with a p-value of 1. With a p-value of 1. So what I did in these 3 little examples, I probably didn't even need the first one, but it's a good, first one's a good way to kind of redirect you. Yeah, you see in the last 2, you see the 2 extremes. So all other examples fall somewhere in the middle, right? But yeah, look at this, okay? When most of the total sum of squares is eaten up within the group, all right? That's very little evidence of any difference between the groups. The one before it, all of the variation was eaten up between the groups, and there was none left within the groups. So hopefully a little more intuitive feel. Now we go back to the mice. All right, so we're home free now. We are, okay? Home free.
Cool.
Ready to go back to the mice. We have our analysis of variance tables. We're done with the number crunching. We are. Okay? Back to the data and the study question. I didn't go to the study question. Is there convincing evidence that the true average time to death for all mice like these is different for the 4 groups? Okay? Is there a difference among the four groups? All right? And we, of course, begin our investigation with, some descriptive plots. Stapler will do that very well, and I'm going to show you how that's done on Stapler. Now, all right, let's start with defining means. Okay? That mu C, mu L, mu M, mu H. Control, low, medium, and high. Give a true mean time to death for mice like these when fed. No, low, medium, and high doses of red fluid. Again, appealing to a population, a mythical population of mice. Right? And we're all set up. So, you know that we're going to test. The null hypothesis says this, yeah, dosage doesn't make a difference. Now, red dye, harmless, right? All the means are the same.
Make your computer easier to
All
use.
means are the same. Versus HA, at least one group differs from the other groups in terms of the mean time to death. At least one group differs. At least one group differs. Okay? Now, that's using the mean, and I thought a lot about this, and I could have stopped right there. Well, and it just kept going with this analysis. But there's also another way to couch this. Generally, as an undergrad stats course, maybe a stats 2 course, that's what you see up top. Okay? But if you're going on to study other types of models, okay, there's one-way analysis of variance, there's two-way analysis of variance, there's two-way analysis of variance with interaction. Okay, then you need to know how to do it this way. And that's the other course I'm doing. It's MAT, I forget the number, but it's statistics with regression, basically. And we do four things really. I did simple linear regression, I did multiple regression, I did analysis of variance, all three of them, all three of the aforementioned, one-way, two-way with interaction. And now we're doing logistic regression, and Tuesday's my last day with them, so I'm going to show them some simulation methods. Yeah.
What? Do you teach that all the time? I didn't know about that one. That sounds like
Sure. A lot of
be
the
useful.
farm folks take that. Down. It's one of those W courses, writing courses.
Oh, the right.
Yeah,
Okay.
I can get you the call number for it. So if I look at Canvas there, it's, one of the.
Or, yeah, I
so-
can
so
check it out.
It really is a cool course.
Yeah.
Really good bunch. It's small, like this. So, in order to kind of raise the bar and study the other models, okay, you have to take, a modeling approach. Okay. So, what I'm saying here, this is another way of couching this. Okay? I'm not going to show you those other models, but if Frank D'Amico goes this route, I want you to be ready for it. So the alternate, the null hypothesis saying that there's no group effect. It just says, oh yeah, the outcome variable, the time to death, it's some function of your grand mean, the true grand mean, or some random error. And the ultimate hypothesis says, no. You got a grand mean, but you also have this group effect. And then some sort of random error. Okay? Where alpha k represents the group mean for the kth group, and that's called the group effect. So what you're testing is whether or not that is there for all four groups. Okay, that's the null hypothesis. For at least one group. The null hypothesis says no, that's not there for any of the groups. So it's alpha C, alpha L, alpha M, alpha H equals 0. Like it's gone, which gives you that. So look at how this differs. Okay, this says basically all the means are the same. Don't put the equals 0 on there because you're saying all the means are 0. Now, okay, this one's saying the group effect is nil. Yeah, it's just not there. Versus, at least one of those group effects is there. It's there for at least one of the groups. So this is kind of the traditional undergrad biostats 2 way of doing it. I'm sure, I'm not checked with them, but I'm sure that's the way Sean Tierney does it. And that's kind of a big boy, big girl, getting ready for other models type of thing. So I've written this up both ways. Okay? We're going to perform an analysis of variance. Okay? And the model says that the response is an accumulated sum of the grand mean, the group effect, and some sort of random error. So you've got parameters here. You've got parameters. As always, we need to talk about the conditions. By the way, in the take-home final, I'm not sure if you've read through it yet, but in most, if not all of the problems, I say, yeah, assume the conditions are met. Okay? Yeah. We assume that the random error terms must have a mean of 0. Okay? They're distributed equally. They go plus or minus with equal probability. The error terms must have the same standard deviation for each group. And it's commonly referred to as the equal variance condition or homoscedasticity. I don't even think I pronounced that right. Homoscedasticity. I always have trouble around here. Homoscedasticity.
Let's call it as homo.
Right. I messed it up there. I don't know. The error term follows a normal distribution, and they must be independent of each other. So we kind of can package the first 3 up like this. Ooh, errors are approximately normally distributed with a mean of 0 and a standard deviation sigma sub e, which is applied to be a constant, and then we just tack on this like, yeah, they're independent of 0. Okay, let's make you a shorthand for all of them. So those are the conditions. Back to the data, okay? Back to our model, okay? And we have parameters. So now we want to kind of estimate the parameters from sample data. How do we estimate that grand mean? That's pretty easy. Take the mean of all the data, okay? How do we estimate the group effect? All right. Take each group mean, but remove the grand mean, okay? And that's another parameter right there, the error term. How do we do that? Okay. We take the actual value and we subtract the group mean. Group mean. Okay. So here, let's do exactly that. Yeah. Let's do exactly that. Let's find these parameters. This will be easy. Okay. So let's find estimates for each of these parameters. Well, alpha, medium, alpha, high. Let's pick 1 or 2 values and do epsilon. Okay, the error, where it's going to be the value minus the K mean. Okay, you could go up. You could go up here. Yeah, everything's right there. Grand mean 75. So, yeah, you want to estimate the population grand mean. Use the sample grand mean. Ooh, I'll do this. Y bar is 75. Okay. You want to estimate each of the group effects. All right. Well, start with the group means of 90, 70, 71, and 65. And subtract off the grand mean. Okay. And that's what? 15, and that's -5, and that's -4, and that's 10, -10. Right? Did I get that right? arithmetic right there.
Yes.
15, -5, -4, and 10, -10. All right. If you would like to get the, let's say for y equals 69, the estimate of the error term, well, that is going to be 69 minus the group mean of 90, which would be what, -21. All right. Yeah, I debated putting that one on there. You don't necessarily need to know that. But what I would like to convince you of, okay? I would like to convince you that, now, convince yourself that mu hat equals, okay, the, is the sum of these three. Sure, I'll show you. Yeah, I'll show you. I'll do it for the control group. I'll do it for the control group. Let me start with this. Okay. Oh, there we go. That's my bar. Okay. This one is going to be y, the control average, minus y bar. And the epsilon for any member of that group is going to be y minus the control mean. Okay, well, check it out. That cancels with that, and this cancels with this, and you're left with y. Yeah, so it kind of worked backwards. I started with this and showed you that as y. Yep, that is how we break it down. Again, this is kind of the more theoretical way of looking at it, but it's necessary to go on to other models. Just before I press on, let me just share a little with you about what these other models are. This is our model, okay? You have the response variable. You've got a grand mean. You've got a group mean. And you've got an error term. Oops, sorry. Yep, that's the rest of it. Okay. All right, that's one-way analysis of variance. Two-way analysis of variance, you've got two factors. You got two factors, okay? Let's see, maybe the factors are, in this one, factor one is the dosage. Maybe the second factor is the gender of the mouse. Yeah, that's a good one. The gender of a mouse, okay? And maybe the female mice reacted differently. So you put that one in, we'll make that a J. Okay? So that's a two-factor analysis of variance. Now, the third model is a two-way with interaction. Okay? Yeah. This one says, yeah, maybe the female mice reacted differently. Okay? This one is a gamma subscripted kj, and that's an interaction effect. You know, did the female mice react differently to maybe some of the higher doses? Just with these two, it says, okay, maybe the female mice reacted differently across all the doses. But this one says, no, males and females were fine. Well, there might have been a difference between males and females, but the difference was greater for the higher doses. Yeah, and that's called an interaction effect. So you see how we build our models. And that's what I did in the other class. We started with this one, and then we built the other model, and then we built the other model. And that's really helpful. So just wanted to show you what's out there. All right. Hey, here we go. Drum roll, wrap it up. Let's get to the analysis of variance. What do you need to know? Seriously, what do you need to know to answer the question. Starting right here, you're gonna produce your own analysis of variance table. I'll show you how to do that. And okay, we're gonna test for difference between the two group means. I'm gonna leave it up to you. If you want to do it like that, great. If you want to do it like that, great. Don't care. Don't care. I've provided both. I've provided both. Okay? If you do it this way, the group effect way, here's what you say for HA, at least one of the alpha K's is not 0. If you do it this way, that all the mean responses are the same, you say, at least 2 of the means are different from each other. And then you produce your pretty little analysis of variance. Finally, for the first time, okay, here it is, okay, SS total, SS groups, SSE, error, error sum of squares. Some books call it between within total, some books call it model error total. But here it is, K minus 1, N minus K, and N minus 1. We know how to do that, we know how to do that, okay? Yeah. P-value calculated from the F statistic. All right. We've already done this. We've already done the ANOVA table. We'll just go right to here. We already did it. Yeah. There it is. And here it is from start to finish. Okay, the complete ANOVA. Once again, I'm doing it both ways. All right. And you just pick one. Okay. Here I define the mean, up there I define the group effect. Here I define the means. There's your 2 versions of HO. There's your 2 versions of HA. Test statistic, all you have to do, write down the test statistic with the p-value. The p-value is 0.032. Because the p-value is less than 0.05, the null hypothesis is rejected. Now, careful of your conclusion. All right? Now, which one am I going with? If you're going with the group effect, you say, okay, 5% level of significance, there is convincing evidence that the group effect is significant for at least one of the groups. If you're going with this one, you say, 5% level of significance, there's convincing evidence that the treatment time to death for all mice like these is different for at least 2 of the groups. Okay, that one differs from at least one of the other groups, right? So it's different for at least 2 of the groups. And that's what you do. Yeah. And that's it. I've actually given you this one. Okay. The sample sizes are all the same. We're testing 4 different methods of reading. And so yeah, really all you have to do is load it in to yeah, I'll show you now. Okay. I sent you, well no, I don't know, I didn't send it, I posted it to the Canvas. It's an Excel file. I think the second tab has this. So here we go. Let's go back into Statlet, go back to the main menu. Where do you want to go? Okay. 2 quantitative variables. No, wrong, sorry. No, I gotta remember where to go. Oh, yes, sorry. 1 quantitative variable, multiple groups. Yeah, so you only have 1 variable, time to death. So I'm gonna name it time to death. Time to death in days. Now I got 4 groups, so you see this little tab here? I'm gonna add a group, add a group, add a group. I'm gonna give the group names. You got their control. Okay, you got your low dose. You got your medium dose. You got your high dose. Now, I'm going to come down here, I'm going to grab each of the 4 columns. Here's the first one. Here's the first one. Paste it right there. Grab the second one. Paste it right there. Here's the third one. Grab it. 30 seconds? Oh, I'm sorry, let me pull that down for you. Hey, got a little third shot. There we go. And then it'll do all sorts of pretty things. Remember those dot plots I produced? Yeah, begin analysis. There's those dot plots I produced. Oh my gosh, so many pretty things. There's a dot plot of the data. There's a summary of the data. There's your sample size, mean, standard deviation, and the 5-number summary, minimum, Q1, median, Q3, and max. All right. Perform inference. Right here. There is our analysis of variance table. This one, I've seen some books do this. Not a big deal. But this one lists the degrees of freedom first and then sum of squares. I kind of like it the other way around because you just say this divided by this is this. Okay, whatever. You list the degrees of freedom first. All right. Big deal. Mean square this, F value, P value. That's how you do it. That's how you do it. I show you on Excel. Because after all, it's an Excel spreadsheet. It's sitting right there. Okay. So I don't. Yeah, I think I've done this. That you go to data, and you're looking for data analysis, which I don't see it. So you have to add it in. Did I do this with the other group? Watch carefully, and I can walk you through this. It's an add-in. I have to do it every time. For your file, okay. Down the bottom, options. Okay. Now that says add-ins right there. I'm going to add in the data package, and it's in there, right? And it's right down here. Ooh, Excel add-ins. I said, yeah, go. Go for it. And then you check those little boxes. I don't know the difference between them. I just check them both. Yep. And press OK. And we'll have it. Ooh, there it is. Data analysis right there under the Data tab. So I press that. And it is the top one, very top, top one, as they're in alphabetical order. By the way, I talked about the 3 models. There they are, right there. Yeah, Staplet doesn't do the other 2. Doesn't do the other 2. But single factor. So they want the input range. Okay. Here, before I do that, I'm going to put in column labels. Here, I'm going to get out of that for a minute. I'm going to put in some column labels. Okay. I'll call it control, low, medium, high. Okay, let's do it again. Data analysis, ANOVA. Input range, I start up here with the column headings, and I just sweep it out. So don't worry about the blanks that I've swept out. It's not going to interpret them as zeros. Interpret them as blanks. And then it asks, ooh, you have labels in the top row? Yeah, I do, yeah. Don't treat it as a value. And where do you want your left-hand corner of the output? Put it right there. Put it right there. Boom, there we go. All right, look at the pretty thing. See, now Excel does its sum of squares and degrees of freedom. Yeah. Yeah. So anyway, this is what appears in your notes. Yeah. Because I like that. Because I like that. Counts and sums and average and variance, and there's your analysis of variance. Don't worry about F critical value. Nobody uses that anymore. Yeah. Basically, if I go, folks. That's the first of a couple of things I wanted to do with the analysis of variance. So that's the very last question. Just produce the ANOVA table, do a start to finish ANOVA. Shouldn't be hard at all. Anything about that? I'm going to take a little bit of a break. And actually, I want to get the regression notes. I want to make sure my PowerPoint agrees with my notes. I meant to check that. I meant to check it. So, all right, take a break. I'll be right back.
That's pretty neat.
That's fine.
Only funny what you man, I'm taking my way. Like you don't like us, like I'm putting over us.
You're writing about being in the country. I'm parents when it's like this. Good. Everyone, you can't escape it. Like, why? I'm close by.
I mean, that was basically my hometown, which I've now returned to since graduating.
Yeah.
And graduated.
Like, I don't know if it's identity. Just, I feel like, I like it. But I support her and I support that.
That's fair.
But
That's
yeah,
fair.
literally everyone.
Honestly, I wouldn't dispute that. Just saying use software.
Oh, here's another. I think they're everywhere.
Yeah, just because we're obviously. Okay. Yeah, just because we're using software for all of this. Just gotta make sure we're precise with our language on things. Which should be.
Letters. It's good. I think punching like this hurts worse. Do we have this conversation?
You definitely mentioned it.
If I was more punch like that, that would hurt. This can't hurt. Something like that would hurt nothing.
But each person.
All right, we got this nice little handout with the
That was
promise that hangs on here. Hopefully, I've changed this data set so many times, but, let's see.
Dr. Bush, are we going to get back?
Oh, that's right, I'm sorry. I think I left it in my office.
Okay.
So if you, I want you to get back everything, but if you really want it for this thing, let me know, I'll scan it and send it. Yeah, cool, yeah. Yeah, let's look at little comments that, this is a really neat example. Very kind of simple. And, once again, I've used this a lot, in my little AP workshops. Yeah, correlation and linear regression. So right away, this just introduced the. That's interesting. Got misplaced there. Let me just check here. So our little example has a series of trains. They're running from Oklahoma City to Omaha. And each time it runs, okay, it's hauling not the same number of rail cars. The number of rail cars vary, as does the fuel consumption. Makes perfect sense, right? The longer the train, the larger the fuel consumption. Sure. If you have a 4x4 truck, you know that you're not going to get great gas mileage if you're on a refrigerator from Pennsylvania. So we want to look at the relationship between the number of rail cars and fuel consumption. The first thing we do is we construct a scatter plot. Again, I'll show you how Statlet does it and how Excel does it. I stay with the Statlet on this one. So we plotted the points. There's 20, 58. 20, 58 is probably that one right there. Looks like there's another 20. Oh, the two in a row there. Oh, 52. Oh, yeah, okay. So that's the 58 and that's the 52. And we do see that there's this upward trend of supporting our theory that the more rail cars there are. What I want to do quickly is I want to compare the data set on here to what's on here. Oh, good. Good. Yes. That's the most recent one. That was produced by Excel, right? What we're going to need these multiple R squared, not this one. We're going to need this one, and there are 10 observations. But we'll tell you about that as we go along. This is just some of the outputs that you're going to get. Woohoo! There's an analysis variance table. Okay, what's that about? Well, at least now you're familiar with it. Right? And that's interesting. That's Excel, and Excel put the degrees of freedom on that one first. Okay. This is a little report on the estimates of the parameters for the least squares regression line. So what we're going to do is we're going to start interpreting the scatter plot. Part A, I'm going to interpret the scatter plot. And when you interpret the scatter plot, okay, here's your classic interpretation. You want to address strength, direction, and form. Strength, direction, and form, and have it all in context. Okay. Long. Okay, let's do a pretty tight fit there. Needs to be close to an imaginary line, as opposed to some adjectives like weak or moderate. Positive is pretty easy. Positive means it's going up. As the number of rail cars increase, the fuel consumption increase. And it looks linear. It looks linear. You say, well, as opposed to what? Sure. As opposed to nonlinear. There's a little curvature to it. But yeah, that's your classic interpretation. The scatter plot indicates a strong positive linear relationship between the number of rail cars and fuel consumption. Instead, you want to look at the overall pattern, you want to comment on the strength, you want to comment on the direction, and you want to comment on the form. Look at it for any outliers too. If you see any outliers, okay, comment on that. Okay. All right. Maybe there's a train down there. Okay. Particularly late train. And always include context. Okay. That's part A. Now we get to something called the correlation coefficient. Okay. Otherwise just known as the correlation. Now, this is a measure of strength. Yeah. So we have a parameter, your population correlation, okay? That's rho. And really, it's the product of the z-scores for both number of rail cars and fuel consumption. Okay, take each pair, number of rail cars and fuel consumption, change them into z-scores, multiply them together, add them all up and divide by however many pairs you have. And that is the population parameter. Now we deal with the statistic. Okay? It's a sample mean, sample standard deviation. And we calculate the z-scores, and we multiply them together and add them all up and divide by your traditional n minus 1. That's little r. And you're not going to have to do that by hand. No. Nope. But correlation makes no distinction between which is the explanatory variable and which is the response variable. Now, in our study, the explanatory variable is number of rail cars. Because we think that the number of rail cars explains the fuel consumption. Hey, how did this train burn up so much fuel? Oh, I can explain that. It had a lot of rail cars. Right? And yeah, correlation makes no difference. So, the correlation between the number of rail cars and fuel consumption is the same as the correlation between the fuel consumption and the number of rail cars. Now, the correlation, as you saw, uses standardized scores. Yeah? And you know that standardized scores have no units, right? Units, number of rail cars minus number of rail cars divided by standard deviation, number of rail cars. Units cancel. Okay? Yeah. The rail cars, they all cancel. Correlation has no units, which is really cool actually, because it means that you can change your units. Okay? Yeah, let's say that you're doing a correlation between height and weight. For height, you can use inches or centimeters or fractions of a mile. For weight, you can use pounds or fractions of a ton. It doesn't matter. Correlation is never going to change. Positive correlations indicate, okay, a positive relation between the variables. High-low values of x are associated with high-low values of y. And negative correlations indicate a negative relationship, negative association. High-low values of x are associated with low-high values of y. Correlation is always a number between -1 and 1. Always. Correlations near 0 indicate a weak linear relationship. And the strength of a linear relationship increases as r moves away from 0 and towards either plus or minus 1. Okay. Sorry. Yeah.
Minus 1 is also strong?
What's that?
Minus 1 is also strong?
Yeah. Yeah. We're going to play a game.
Is there anything different, right?
What's that?
More than different is strong.
Here, I'll show you. Okay. Come on. There we go. Correlation guessing game. Okay. Now, my only regret is this is a little small. There's a little game here. I'm going to make my first example kind of easy. Oh, that's a really easy one. Okay. So, all right. Correlations are always between -1 and 1. When it's exactly 1, the points lie exactly along the straight line with a positive slope. -1, they lie along a straight line with a negative slope. That one's pretty easy. They're not exactly on a straight line, but they're really, really close. I'm going to guess the correlation is 0.97. That's my official guess.
9.3.
Do you agree? Oh, it's 0.991.
Oh, wow.
Wow, okay. Reset. New sample. Okay. Also pretty strong. Not as strong as the last one, right? Not as strong as the last one, it's pretty strong. I'm still gonna say it's in the negative 0.9. Okay? Yeah, 0.9, negative 0.975. Okay, also negative, not near quite as strong. And I see a couple of them off the pattern here. We're gonna mess it up a little. Not that good at this, but you know, but it's kind of like that. Let's say it's in the negative 0.8s, maybe negative 0.85, maybe. Oh no, a little weaker than that, negative 0.768. Okay, now there we have a positive correlation. Kind of gets easier the more examples you see. Positive and, those road ones from the last one, that might be about the same, maybe 0.7. 0.78. Okay, that's stronger than I thought. Oh, okay. Ooh. Oh boy. Now I do see a positive trend. I do see one. I don't know. This is where it gets tough. You decide in your head, maybe 0.4. 0.304. Yeah. Oh boy, that's even worse. I don't know. 0.2. 0.222. Okay. A couple more here. Another weak one. Yeah, I was going to say about the same as the other one. Oh, that one's all over the place. We'll probably end with that one. Jeez. Oh my gosh. I mean, is it going up? Is it going down? Oh yeah. It's a good one to end on because I'm going to say that's really close to zero. I don't even know if it's positive or negative. 0.173. Yeah, pretty weak. So anyway, that little game gives you a little insight into and how this correlation goes. Right? Yeah, there's the applet that I was using there. And there's a rough guide of what you call it. No relation, very weak, moderate, strong, very strong, perfect, positive relation. Yeah. Little rough guide. A rough guide. All right, so this one, and I'm going to show you where to get these. This one's very strong, right? 0.9836. It's really strong. Okay. So we say because the correlation is close to 1, there is evidence that the linear relation between the number of rail cars and the fuel consumption is very strong and positive. So we lead with that. It kind of does look like an interpretation of scatter plot, but a correlation comments on the linear relation. Hey, how is that linear relation? Huh? How's that linear relation between the number of rail cars and fuel consumption? Okay, the linear relation, it's very strong and positive. Yeah. So, yeah, again, it really helps quantify the strain. When we interpreted the scatter plot, it was easy to show direction, okay? Linear, because it looked at it, but this helps us out with strain.
So, Dr. Bush, with non-parametric models of
Yeah.
I guess would the correlation be less useful and the R squared would be more useful for a non-parametric? Or can you still look at the
Yeah, R
correlation of
squared is
R?
gonna be something different. Yeah, we're gonna look at R squared. Yeah.
Well, I'm just meaning like since a non-parametric, it's not measuring or commenting on the linear relation for
I
a
see.
non-parametric.
I see, like your Spearman's rank
Yeah,
correlation.
something like that.
Yes, yes. No, you still interpret it the same way.
Okay.
Yeah, it's still interpreted the same way. It's just a different way of measuring it. Yeah. All right, so now we're ready to introduce the model. the model that we're going to use. And we're going to use this for a lot. But I wanted to talk a little about modeling in general. If you actually saw it in ANOVA, okay, but what you're doing is you're taking the response variable and saying, yeah, the response variable is some function of x, okay, the explanatory variable, number of rail cars, plus some random error. And it's just a matter of what type of function you pick. You can pick a linear model, which we're going to do. And this is what we're going to call the parameters, beta 0 and beta 1. Beta 0 is going to be our intercept, beta 1 is our slope. Like in old algebra, y equals mx plus b. Okay, the m is the slope. It's going to be beta 1 here, beta 0 here. So yeah, you can use a linear model, use a quadratic model. You can use a power model. You can use an exponential model. These are all models that are used. And you touch upon them in that other class. But we're going to keep it simple. I'll start somewhere. Let's start with a linear model. Data suggested a linear model. That's pretty much why we're going for it. The assumption, the conditions are much the same as what I showed you for ANOVA. But the error terms. We require that the error terms have a normal distribution with a mean of 0 and a constant standard deviation, okay, across all levels of x. So really there are three parameters. Yeah. Beta 0, beta 1, the intercept and the slope, and this common standard deviation. Yeah. There are three parameters, but only two in the model. So we're going to estimate beta 0 and beta 1. And now I'm gonna just creep into calculus land a little. I just want to, so those who've had calculus, I want you to know where these estimates come from. Okay. Our objective is to minimize the errors, the sum of the squares of the errors. Yeah. To make this quantity as low as possible. We call it error sum of squares or sum of squared errors. Okay. Now remember, okay, the errors is y equals beta 0 plus beta 1x plus the error. So when I solve for error, I get y1 minus beta 0. That should be a plus. That should be a plus, which is correct there. That should be a plus. I don't think I can fix that here. I don't think I can fix that. Yeah, that is a screenshot, so I cannot fix that. But it is correct in the next line. Yeah, that is correct. Okay. What you do, think back to your calculus. If you want to minimize or maximize something, you take the derivative, you set it equal to 0. Derivative with respect to what? Because we have two parameters. So we take the derivative, and it's actually a partial derivative with respect to beta 0. And it's power rule. Add the power, subtract 1 from the power, and the derivative of the inside, the partial derivative with respect to beta 0. Okay. You set that equal to 0, and at the same time, all right, there I'm setting it equal to 0. Okay. And I get a nice little equation there. And then I do the same thing. I take the partial with respect to beta 1. Okay, after the chain rule, taking the derivative with respect to beta 1, I get this factor. And set it equal to 0. Alpha there. And what I have are two equations and two unknowns. We know n, and we know the sum of the x's. That would be the sum of the number of rail cars. We know the sum of the fuel consumption. There's that again. We know the sum of the squares of the fuel consumption. And that's the product of the number of rail cars and fuel consumption. So we have a simple linear system We really do, and then matrix work takes over, or you just get out your calculator and solve it. So I don't want to go too deep into that, but I want you to see a little bit of where it comes from.
Is that the, also called like the decoupling process? Is that? Okay.
Exactly. Yep. Yep. So,
Same.
after solving and a bunch of algebra, that if this were a theory course, I would very carefully bring you through, but you can show that the estimate of the slope very simply is this. Standard deviation of the y divided by standard deviation of the x's times the correlation. Wow. It all boils down to that. By the way, any AP stats kid, well, any AP stats kid who's destined to do fairly well on the exam can tell you this relationship. Yeah, they can tell you that relationship. Yep. And I've seen a couple of AP stats problems in the past that depend on the kid using that relationship. And then beta, the estimate for the intercept is that. So gang, all you need to know to get these estimates is the mean of both x and y, the standard deviation of both x and y, and the correlation. Notice, of course, that this depends on finding this first. But it's even better than that. The output gives it to you. It gives it to you. So, here's what we know so far. The mean of x and y, and the standard deviations, there's the correlation. There's the formula. For beta 1 had the estimate of the slope and the estimate of the intercept. And use it. Yeah. And that's our prediction model. There's my slope. 2.1495. All I did took the ratio of the standard deviations and multiplied it by the correlation. Find the intercept. Get the average of the y's. Subtract the product of the estimate of the slope and the average of the x's. Yep. That is our model. I'm gonna start keeping track of some of this stuff that we will need in the long run. Let's start keeping track of this stuff. Right? Well, the correlation. Yep. The correlation. 93836. 9836. The estimate of the slope and the estimate of the y-intercept. 2.1495. Yay. And 0.6778. Yep. So what have I done so far? Really just told you where those numbers come from. Same as I did with analysis and variance. Okay. Now, I am ready to write the equation of the least squares regression line. Okay. And why are those numbers different? Why are those numbers different? Oh, no. Did I? Oh, yeah, that's not correct at all. There's a 10 missing there, right? There's a 10 missing. Yeah, so I didn't put in a 1.
10.6768.
Yeah. Yep. All right, couple of fixes I gotta make on that. But yeah, there it is right there. Now, here's my big joke. Been teaching basic stats for I don't know how long, and I do this. Exams, they have to write the equation of the least squares regression line. Never had a class where everyone does it correctly. Never had one. I tell you, and I use the same standards that we use on AP. I'll tell you where the source of errors come from, 2.1495. Never, ever, ever had a class where everybody has it correct. Okay? What you gotta do, okay, write it down. You have to tell whoever's looking at it what variable is which. Where X is the number of rail cars for a train traveling along the route between Oklahoma City and Omaha. Okay? Or I would just accept the number of rail cars. That's fine. And Y is the fuel consumption. Yeah. That's all they gotta do. That's all they gotta do. But that's the most common error. They leave off the context. And I even tell them, I've never had a class to get it right because everybody leaves off the not a lot of, if you're gonna get it wrong, people that get it wrong, they leave off the context. And then you've got those who have the context, but they get them reversed. Right? They say, why is the number of rail cars next is fuel consumption? No, it's the other way around. The other error that they make, you gotta have the Y hat on there. That means predicted fuel consumption. If you remove the hat, that's a major error. Because Y is the actual fuel consumption. You're telling me that I can get the actual true to God fuel consumption by just using this formula. Wow, a lot of engineers are gonna wanna meet you. Okay, if that's true. It's the predicted, so yeah. Same on the AP exam, same in the classes. I've never, ever, ever had a class where everyone responded to that correctly. So most important, when you write it down, make sure that you indicate, oh, here's what's also acceptable, just for the record on the AP exam. You could say, you could write this, fuel consumption, and they could put a little hat over it, is 10.6778 plus 2.1495 times number of cars. That's fine. That's fine. They got the hat there, they're indicating predicted fuel consumption. We clearly have the context. That is 100% acceptable on the AP exam. Yep. So, now we're gonna have fun with it. Identify the slope. Yeah, and interpret it. Well, we know what the slope is, 2.1495. So what that means, every time you tack on another rail car, now this is important, the predicted fuel consumption increases by 2.1495 units per mile. You gotta have the word predicted in there. Right? You take away the predicted, same errors over there. Oh yeah, for every one additional rail car, the fuel consumption increases by 2.1495. Really, that precise? You can tell me that precise, huh? Really? That's the predicted one. There are other acceptable interpretations. Here's one of them. I like to just pick one and stick with it. Another one is for every additional rail car, for every one additional rail car, okay, on average, the fuel consumption increases by 2.1495 units per mile. So you can eliminate the word predicted and replace with on average, the fuel consumption increases by about. So that is also acceptable. I like that one because it speaks right to this equation. Yeah, remember your slope. Your slope from algebra is rise over run. All right. Well, in here it's not y, but it's y hat. So it's the change in the predicted value of y per unit change in x. Yeah. The reason I love this example, there's a lot of examples that don't have a nicely interpretable intercept. This one does. This one does. Now, what is the y-intercept? When x is equal to 0, right? And our intercept is 10.677, right? Close to 10.678, okay? For a rail car for a train with no rail cars, just the engine, right? Just the engine. The predicted fuel consumption is 10.677 units per mile. So for a train that's just, it's the engine running, right? It's not hauling anything. It's 0 rail cars. Okay, we're not counting the engine. It should be totally that. Okay. Fantastic, let's use it now. We've worked hard to get this darn thing. Let's predict the fuel consumption for a train with 30 rail cars. All right, plug them in, plug them out. I predict, and once again, I have words, I have its symbols. Predicted fuel consumption. Do not hit for the actual one. It's 75, roughly 75 liters per mile. Hey, we're going to use this thing now. It's great. Yay. All right. Would it be reasonable to use the bitter regression equation to predict fuel consumption for a train on this road at 65? Let's see. The longest train was 50. Okay? The longest train was 50. And we've got this nice little regression line that's up to 50. 65 is up here. So I would have to extrapolate. I have to extrapolate. We're allowed to extrapolate a little bit. A little bit. I'm going to say that the longest train has 50 rail cars. And predicting the fuel consumption for a train with 65 rail cars, well, that's extrapolation. Okay? It's generally unwise to use the model to predict fuel consumption for trains with more than 50 rail cars. Your estimation is less reliable. Why? Simply, I don't have any evidence that that linear trend will continue. Yeah, I really don't. Maybe it goes like this. Maybe it goes like that, and ultimately it flattens out. Or maybe it goes the other way. I don't know. I don't know. I can do it. I can put 65 in there, I can do it. Yeah, we generally put up a little red flag. Yeah, I kind of think, okay, we'll do it, but yeah, we're not comfortable with it. That's the point of that. Just watch out for extrapolation. We kind of don't like it. All right. So that's some of the neat things we can do with that. Now, where are we in the whole line of things here? Residuals. Residuals, right? Let's see. Yep. You're following along here. We just did G. Yeah, residuals. Sure. It's the leftover. It's the leftover, a residual. Okay, a residual is the actual value minus the predicted value, which is also known as your error term. The actual minus the predicted. Like that. Yeah, because no model works perfectly. Yeah. There I've calculated, here's a, height, okay. Yeah, height, number of rail cars, yeah, I knew this one needed some fixing. And number of rail cars, does it say there? Yeah, it's that number of rail cars. Actual fuel consumption, predicted fuel consumption, okay? And now the residual, yeah. What I used is I used the model to get all of these, and then I went this minus this is this, okay? This minus this is this. So 58 minus 53.67, let's see, that's 4.33, right? 4.33. And the bottom one is, negative 83.01. So a positive means that there was an underestimate, and a negative means that there was an overestimate. And that's what a residual is. Very simple. About residuals, right? It is the vertical distance. Let's clean this up a little. A residual is the vertical distance between the actual value and the least squares regression line. There's the line. There's the actual value. Okay. Here's predicted value. And that's the residual. Yeah, that vertical distance. Wow. That's exactly the type of thing that we minimize when we derive everything. The sum of the squares of the errors. Residuals are the errors, to be clear. Yeah. So the least squares regression line is such that the sum of the squares of the residuals is a minimum. All we're doing is kind of cleaning up our language. The sum of the actual y values is always equal to the sum of the predicted y values. I don't know if you noticed that, actually. They are, yes, right, yes. Mm-hmm. Sum of the actual y values is equal to the sum of the predicted y values. And the sum of the residuals is always 0, barring any rounding. Yeah. That's the way it's made. Always. Would a negative residual mean our model overpredicts or underpredicts? Well, if the residual is less than 0, means that y minus y hat is less than 0. If y is less than y hat, that's the actual, and that's the predicted. So the actual is less than the predicted. So let's say the predicted is greater than the actual. Predicted is greater than the actual, you got an overestimate. Yeah. Yep. An overestimate. Yeah. Calculate the residual for the last train on the list. Okay, we kind of did that, but here's the math behind that. Last train has an actual fuel consumption of 70. There's 29 cars. There's the predicted fuel consumption. And the actual minus predicted is this. Yeah, so there's the math behind it. Shows you an actual calculation of the residual. This is a very popular problem on the AP exam. Yeah. Suppose there was a train with 34 rail cars, a new train. 34 rail cars, and we used the model to predict the fuel consumption, and then the train actually makes us run. We compare the predicted to the actual, and we find out the residual is negative 1.67. Calculate the actual fuel consumption. Okay? So we kind of back engineer this. So if the train has 34 rail cars, we can get the predicted fuel consumption. Okay. So now we have the residual. We have the predicted fuel consumption. And we want the actual fuel consumption. So we'll just add 83.76 to both sides. 0.76's canceled. And yeah, train it 82. And actual fuel consumption 82 units per mile. So yeah, that's a very, very common exercise. Here's the multiple choice section. What else can we do with the residual? Okay, this is really interesting because what else can we do with the residuals? Right? We make a residual plot. And that's one of the tools we use to assess the appropriateness of the model. Okay? So So a residual plot is a plot of either x or y hat. Okay? Usually at the undergrad level, it's x, but for more advanced courses, when you do multiple regression, we use y hat along the horizontal axis and the residuals along the vertical axis. Right, so there is a residual plot. Yeah, I just plotted residuals. Okay. Number of rail. No, this would be. I did that. I did the predicted. I did the y hats on this one. Okay. I think I might have used Desmos for this thing. I forget which one I used. Looks like a Desmos type of thing. And there's the residuals. Well, actually, it looks more like Excel. I made that with Excel. All right. So, right there. Okay. For the shortest train, or one of the shortest trains. That's one of the residuals. That's another one of the residuals. Okay. That actually looks like this. No, the smallest residual would be here. Largest is put over here. Okay. Yeah. So what do we look for in the residual plot? Okay. We look for random scatter. That's what we're looking for. Total random scatter. That is validation that we've made a good choice. You see, any pattern whatsoever, not a good choice. Not a good choice for linear model. We look for random scatter, residuals, in somewhat uniform band on either side of the scale. That's what we're looking for. See, if your original scatter plot has a curved pattern to it, and you try to fit a straight line, literally or figuratively a square peg in a round hole, you can see the residuals. Look at this. Look at this. Okay? The residuals, now residuals are actual minus predicted. Actual minus predicted. So, all right? So negative residuals, and positive, 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 positive. You're above the line, and negative. Okay? You shouldn't see a pattern there. Okay? You should be either above or below the line in a random manner. See? And the residual plot will bear that pattern out. Now, presumably, you would have seen it in the original scatter plot, but if you didn't, okay, you might see it in the residual.
So yeah, the uniform, good, but the pattern or trend, not yet.
Right.
That's where you're missing it.
Right. You said something key though. All right. Here's another thing to look out for. Remember the condition that the variation in the errors should be the same
It should be the
for all
same.
values of X?
Can't have any.
Look at this, friends. Look at this. We call it a fanning out pattern. Look at that. Okay? Look at that. So that violates one of the conditions. There seems to be more variation in the errors for high values of X than for low values of X. In other words, this model, and this is just a hypothetical here, but this model works really, really well for low values of X. Small residuals, we like small residuals. It's a lousy model for large values of X. No, shouldn't see that. We like uniform, ideally, we like to see a somewhat uniform band. That's pretty ideal. So we only have 10 traits. Yeah, so not a lot we can tell. Yeah, not a lot we can tell. Look for points with large residuals, those are outliers. Look for individual points that are extreme in the X direction. I'm going to show you that on Desmos. They might not have large residuals, but they are called influential observations. Yeah, I'm going to show you that. Desmos has a really cool way of looking at this. don't think I have everything that I can grab the data with, so I'm actually gonna have to put it in here, it's not gonna take me long. 20, 20, 37, make sure I'm typing it in there, 31, 47, 43, 39, 50. Okay, 40 and 29. Okay. Corresponding fuel consumption, 58, 52, 91, 80, 114, right? 98, 87, 122, 173. Okay. Let's go into Desmos. Okay, well, right away, let's pull this down. Like, ooh, we got 3D, try it now. All right, fine, I'll show you. Ooh, look at that. I mean, they go z equals x squared plus y cubed. Look at that. Wow. You can grab it. I mean, really. And that's just the tip away. Anyway, see, leave that. We're gonna do a good old regular Desmos. So what I'm gonna do.
It's about time we needed that. Yeah,
Yeah.
that's super helpful.
Yeah, right at the end of my vector calculus class.
Yeah, that's what I was telling
Oh
you.
yeah, I was so excited. All right, so what I did is I copied and pasted the Excel file, and notice it goes X1 and Y1, thus giving you the option of multiple regression lines within the same worksheet. Okay, but there's my greens, and those are my plotted data right there. Now, right down here, right, I need to use, instead of beta 0, beta 1, I need to use like A and B. So the command here is just Y, and I love this, approximately A plus BX. Oh, I have to do 1. But it'll automatically subscript. I love that, because I'm sure they were saying, oh, well, we can't put Y hat, we don't want to be technically wrong. Oh, I love that. Y1 and the little tilde, A plus BX1. Okay. Now what I don't like, I think they should run the line, or at least give you an option of just running it from here to here. They're encouraging extrapolation, but we'll let it go. There's our squared. Ryan was commenting about that. We'll learn about that in a minute. There's your correlation. There's your A, there's your B, okay? And now, look at your residual plot. You can plot the residuals. Now what I'm gonna do, I'm gonna go back out here. I'm going to put in another train. Okay? The train, number of rail cars, I'm just going to make it the average of all the other rail cars. Yes, I know you can't have a fraction of a rail car, but I want you to take a look at this. All right? Let's go back over to Desmos. We're going to get rid of that. Get rid of that, we're gonna put that in. Okay. So, Y is approximately A plus Y1 is approximately A plus BX1. Now, can I remember how to do this? Okay. Remember how to do this. Yeah, there it is. Drag. Alright. Let's see. I'm looking for 35. Yeah, there it is. 35. Right there. Yes, okay, all right. So I took that extra rail car. Now watch this. I'm gonna go straight up. Instead of looking at the numbers, just look at the line. I'm trying to go straight up. There's not too much of a change. Correlation is decreasing. It's an outlier in the Y direction. So this would be a train with an average number of rail cars, but obviously carrying something really heavy because the fuel consumption is unusually high. But it's not having that much effect on the slope. Oops, that was me. Okay. Now, it is lifting the line up so that the intercept is a little more. All right, I'm going to come back down. Try my best to come straight down. All right, now I'm going to go in the other direction. I'm going to go over in the X direction. Okay? So what I'll have eventually when I get way over there is a train with a really long train, but the fuel consumption is average. So it must be like, you know, hauling pillows or something like that. I don't know. But watch this. Watch it. Oh my gosh. Woo! That is called an influential point. So what you want to watch out for are points where X is really big compared to all the others, and Y is kind of average. So yeah, so this is an outlier in the X direction, and big change to slope. An outlier in the Y direction, not much to change to a slope, right? Now let me do one more. Let's come back here. Now I'm gonna travel along this line. As long as I stay the course. It changes to the slope, right? But the correlation is increasing. I don't know if you can see that. The correlation is growing and growing and growing. It's at 0.9906, 07, 991, 992. Because it's adding evidence towards the linear model. You know, at first it's, oh yeah, it works for these, but now, oh, look at this one. It really fits the pattern there too. So anyway, that's the effect that an outlier can have. Again, outlier in the Y direction, yeah, not much effect on the slope. Correlation decreases, lifts the intercept a little. Outlier in the X direction, whoa, we don't like that at all. Yikes. Look at like a little magnet, right? A little magnet. And then outlier in both the X and the Y direction, keeping the pattern. Yeah. So I love Desmos for that little trick right there. Very neat to see. Very neat to see. Okay. Where are we? We are we in our little travels here.
So, brother, how did you approximate the object?
Was that?
Y equals to how did you go back to the decimal?
Oops. Yeah. Yep. Did I get rid of it? Jeff, you think I got rid of it? Oh, no.
On problem.
Oh yeah, right over there. Yes.
How did you get this y1 equals to?
Sure. Sure. Yeah. I typed that in. That symbol is up in the left upper corner.
Right above tab.
Right. Yeah. That's that one. Okay. Well, that's enough about residuals. That's enough about residuals. Okay. So, touch of. Well, yeah. This one, yeah. I'm gonna say I see random scatter somewhat of a uniform band, that might be an outlier, but we're pretty convinced that our choice of a linear model is perfect, and of course, you know, our scatter plot was quite convincing too. All right. So remember the whole thing with the sum of squares I did with the NOVA? I'm gonna see it again. All right. So knowing that the mean of y is 87.2, what I did is I subtracted y hat from all 10 y values, which would be the numerator of the variance. That's about 18.18. I did the same thing for the y hats. Okay, since the y's and the y hats add up to the same number, I subtracted 87.2 from all the y hats. I got a smaller number because there's less variation in those. Okay, we call that model sum of squares. And then I added up the squares of the error terms, the squares of the residual, the thing that we were minimizing to begin with, and I got 16.91. Same as what I did with the ANOVA, really. And what we notice is the three numbers add up. And that's why you saw a little analysis of variance table. That the total sum of squares equals the model sum of squares plus the error sum of squares. That's why I did them both today. Yeah. Now, like another little game. Okay? Now, keep in mind that we just had right up there a little game. If the model is perfect, in a perfect model, the model is perfect, and all the y hats are the same as all the y's. It's predicted the fuel consumption exactly for all 10 trains. Wow, great. And if that's the case, the residual, which would be the difference between the actual and the predicted, if they're the same, is 0. Yeah. Okay? And that would make, if the residuals are all 0, it's the same as what I did with the analysis of variance thing.
Oh, the
That means
extremes.
the error sum of squares is 0, and all the model sum of squares is the total sum of squares, right? That's 0. And if that's the case, if the model is perfect, divide the model square by the total sum of squares, you get 1. Otherwise, the model sum of squares is always going to be bigger than the total sum of squares is always going to be bigger than your model. Okay? Otherwise, it's going to be less than 1. Okay? That's another thing we use for a measure of how well the model did. Okay? The measure of how well the model works in predicting y is by considering that ratio. Okay? Ideally, we want 1. That ain't going to happen. If this ratio is equal to 1, which in practice never is, then the model works perfectly in predicting y for all the values of x. Okay? When we convert it to a percent, okay, we refer to it as the coefficient of determination. Okay? And it's the percent of variation in the y variable that can be explained by the linear model. Now, it just happens to be, and Ryan, you were alluding to this a little while ago, it happens to be that that ratio is the square of the correlation. Yes, it is. That ain't easy to prove. Okay? That's not quite easy to prove, but it is nonetheless. Yeah, so let's do it. Let's calculate the coefficient of determination from this little breakdown right here. Yeah. All right, it's 0.967. There it is. And 967. It was this number divided by this number. We're can see that the model works pretty well, because there's your total sum of squares, and most of it is taken up by the model, and very little of it is taken up by the error. But the interpretation is even better. Yeah. R squared is 90.967. 96.7% of the total variation. Remember, total variation is down in the denominator. 96.7 can be explained by the linear model that uses the number of rail cars to predict fuel consumption. And the leftover what? 3.3%? Random error. It's a pretty good model. Very good model. Yeah. That is the interpretation of the coefficient of determination. Make sure I'm following along with you here. Yep. Yeah, we did the perfect model thing. Mm-hmm. Yep. Yeah.
Not that it would be any shorter, but it would be the same thing as if you did the error over the total, or you took 1 minus that.
You know what?
Or not error.
And some books define it that way. Thank you. Yeah. R squared is the model sum of squares divided by the total sum of squares. Yeah, it's also, and actually this does appear in multiple regression. Okay, because then you get into something called the adjusted R squared, which actually takes the ratio of the mean squares. So yeah, define in one of those two ways, yeah. Yes.
With that mentality in mind, we would be taking, if we were doing multiple regression, we would be looking at the overall and then taking out the predictors that aren't passing the p-value, et cetera, and then going on individual testing each
Right,
beta cell.
obviously, yeah, you know a great deal about, sure. And that's what I do in the other class with multiple regression. Yeah, you're right, we go far beyond this to test the individual. Because, yeah, in a test of hypothesis, okay, when you test for whether the model is effective, say, okay, yeah, you get a p-value less than 1, yeah, the model is effective. You say, okay, so are there any variables that can be eliminated and still be equally effective? Right, that's where we do the post-analysis. Yeah. Yeah, and here, just verify that the R squared is indeed, yeah, if you take R squared, this R, this is the part that I've always found interesting. Yeah, you get your 0.964. That's the part I always found interesting, that the coefficient of determination is actually the correlation squared, which, again, Ryan, is why in multiple regression, it's capital R. If you ever wondered about that. In simple linear regression, they use little r squared. In multiple regression, they use capital R squared, because there's no analogous relationship in multiple regression. We have many correlations. We have a correlation of y with all the predictor variables. So, yeah, there's no such property in multiple regression. So they make that really clear. They give it a capital R. At least that's the story I'm told. Okay. All right, what about that third parameter? We've been ignoring that third parameter. Okay. Almost done here. That third parameter, okay, the standard deviation of the residuals. Okay. As a parameter, it is called the standard deviation of the residuals. As a population, we're going to estimate that with, we call it either S error or sigma hat error. And we call that the standard error of the residuals. Pretty consistent language, right? Standard deviation, standard error estimates the standard deviation. And what that is the square root of the error sum squared divided by n minus 2. Okay, you lose one for each of the two beta 0 and beta 1 parameters. Okay, so we have 4.3613, okay, given in the output. All right, so here's verification of that. Okay, if I took my SSE divided by n minus 2, I would indeed get that. And the way we interpret it, say typically that vertical distance between the predicted fuel consumption and actual fuel consumption is about 4.361 units per mile. That is a typical deviation from the line. Or typically the predicted fuel consumption numbers differ from the actual fuel consumption numbers by about 4.361. That's really on average. No, don't say on average. Typically, that's the word we use. Typically, how far are you away from it? That is the interpretation of that. Okay. How do we estimate the standard deviation of beta 1? Okay. You need the sum of the squared deviations of the x's, okay? And once you have that, take your standard error of residuals and divide it by that. So here I'm just presenting the formulas. The output shows that. Right here. Output shows it. Right here. Yep. So I just want you to know the formulas. Now, so we asked the question, is there an association between the number of rail cars and fuel consumption? Provide appropriate statistical reports for my answer. We're going to do a formal test, a t-test for slope. Is the slope 0, or is it greater than 0? We're pretty much assuming a positive relationship. Or does the number of rail cars not matter? Well, we know how this is going to play out. Beta 1 is the true slope of the population least squares regression line. Okay? Using fuel consumption and number of rail cars. All right. All conditions are met. I'm not going there. All right. We have a t statistic from the output. All right. And where is the output for you all? Okay, where did I stash that? Okay. Yeah, that is first page to the back side. Yep.
And Dr. Bush, an alternative to this could be testing the population correlation coefficient equal to 0 as well. That would be the
Exactly.
same test.
And those two tests are one and the same.
Okay.
Yep. Yep. Different test statistic, different standard error. Okay. Same result. Same result. Absolutely. Absolutely. Yep. So yeah, the test statistic is right there, the p-value is right there. There's even a little confidence interval type of thing going on there. But here I am just going through the calculations just so you can see. Yeah, there's the output. Yeah, p-value is less than 0.5. So hypothesis is true. There's convincing statistical evidence. Yay. All right. Whew. Couple of more things I want to show you. Okay. R, S, T, and U. We kind of already did U. I want to show you 3 types of confidence intervals, and I did notice that there's a major word correction that needs to be made. Okay. Next, I'm simply going to calculate a 95% confidence interval for the slope. I'll show you 95% confidence interval for the slope. Right. T interval. Right? So I use a T degrees of freedom, 10 minus 2, 8. And there's my standard error with that. So there it is. It's the slope plus or minus the t-value times the standard error. And there it is right there. And we see that 0 is not in there. Okay. We say with 95% confidence that the true slope is somewhere between 1.83 and 2.47. Okay. So that's a confidence interval for slope. Okay. And the output gives you, an Excel output will typically give you a 95% confidence interval. Yep. Now, calculate and interpret a 95% confidence interval for the mean or average fuel consumption. This is the word that needs to be corrected. For all trains with 40 rail cars. All trains. I want you to think about this. You've got trains running back and forth. Okay? I'm interested in only the trains with 40 rail cars. Even there's going to be some random variation in the fuel consumption. All I'm interested in the trains with 40 rail cars. Okay? And I want a confidence interval for the average or mean fuel consumption for all those trains. For all those trains, 40 rail cars. Right? I'm going to need that number. Right? So, right, a confidence interval for the mean response when x takes the value of x star is this, y hat, t critical, standard error of mu hat. There is the formula. Standard error of the residuals, 1 over 10, right? Now that's going to be 40 right there. 40 minus the mean, and then that number right there. Okay, that's the standard error of the residuals. Okay, that is a confidence interval for a mean response. Okay. So yeah, let me be clear on where all of that is. I need the standard error of the residuals, I think. Yes. Wait a second here. There's the okay, yeah. Standard error of the residuals. That was the 4.3613. And then 1 over n. Okay. The 40 minus, and I need the average number of rail cars. Okay, I think that shows on the front page. Had that somewhere.
35.6.
Here is it. It's up here somewhere.
What number was it?
X bar. Right up there.
35.6.
35.6?
Yes.
Oh, were you looking to confirm that?
Yeah, I'm looking for X bar, I can't seem to find it. Oh, 35.6, I found it. Yep, I found it. Yeah, I am on, oh, I do have it written out. There it is.
Yes.
Just not on my slide here. And then over the 976.4. Yep. Yeah, I just wanted to be sure of where that came from. Oh, okay. No, I do have it. It was the next slide. And that together with the t-value, okay, the t-value, right there. So point estimate plus or minus t-value, standard error, margin of error. Yeah. So you say, all right, for a train with 40 rail cars, I can expect it to use between 93 and 100 units per mile. It's not bad, it's pretty tight, Okay. So, one more thing, and then I'm gonna show you how to use Statlet for this. One more thing. Okay, there's my interpretation. Part T, calculate and interpret a 95% prediction interval for the fuel consumption of, and that is correct, of a train. Almost wrote. I did that one time. Of a train with 40 rail cars. Like, okay, there's a train over there. It's got 40 rail cars. That train right there. Let's try to predict the fuel consumption. Great, use the model, but let's put a confidence interval on our prediction. Yeah.
This is
So now it's the same formula, except it's the standard deviation of y hat, which is the identical formula, but you have a little one there. It's a little one. And I could go through the derivation of that, explain where the one came from. So basically, yeah, I'm going to take my work from before. I'm just going to stick a one there. Now, the effect of that one, it really increases the standard error.
Just to confirm the big picture here, the prediction interval, the way you described it was a confidence interval for confidence interval.
No, there's a
Sorry, I might have
confidence
missed
interval
that.
for a single prediction.
Okay.
The train's sitting over in the railway station, and I know it has 40 cars. And I can use the model to predict the fuel consumption, and now I want to put a margin of error on that prediction. That's what I want to do. That's what I want to do. Right? Now, it's pretty wide. It's pretty wide. It's much wider than before. Is it a train sitting over there with 40 rail cars? Yeah. I predict that fuel consumption will be about 96.
yes.
Okay? But you want a 95% confidence interval on that, somewhere between 86 and 107. So we still use the phrase level of confidence. We still use that phrase. But we use the word prediction interval to separate it from a confidence interval for a mean response. So there's two of them. A confidence interval for a mean response and a prediction interval for a single response. So the 95% level of confidence, the fuel consumption for a train with 40 rail cars, 86 and 107 units per mile. Yep. So that's pretty cool. That is a prediction interval. And then this one, I said, suppose there's an 11th train traveling along this route, 60 rail cars. That's a lot bigger than all the rest. But for whatever reason, all the cars are empty, and the fuel consumption is only 90 units per mile. So that was the thing I was telling you about, right? You've got this, and you have this big long train that's done with a bunch of empty cars that describe the effect of including the data on this train on the slope of the intercept. So because its point is outside the pattern of the rest of the data, with exactly what I warned you about, with an x value larger than the rest of them, this point pulls. Remember what happened? It pulled the least squares regression line toward it, increasing the y-intercept, right? Because you're like, brings that left tail up, and decreasing the slope, and now the other points are going to be further away from the line, so the correlation will decrease, and it's just causing a big mess. And that's called an influential point. That's called an influential point. And again, any AP kid who's gonna do well on the exam knows about that. So let me show you. I think Staplet is one of the best ways to go. It gives you everything you need.
I have one quick
Oh,
question.
sure.
In the part C, that with 95% of the confidence, should that statement say the predicted fuel consumption or not? I guess I'm not understanding.
Sure. Part T,
Yes.
yeah.
The
Um,
conclusion.
with a 95% level of confidence, the fuel consumption for a train, okay? No, that is correct, because what we're doing is using that interval to estimate the unknown. We want to estimate the fuel consumption. Now, I could say we predict the fuel consumption to be 96.657. That's our predicted. But we also say that, well, you could say, no, with 95% level of confidence, the fuel consumption will be, and again, that wiggle word that we call it, predict, that's covered by 95% level of confidence.
Okay.
It might, or it might not. The true fuel consumption lies in that interval, 95% of all possible samples, 5% of the time. So yeah, crazy is correct there.
Yes, that's because you are predicting the true. Yes, not the
Yeah.
mean. Yeah.
Train's about to leave the station, and when they get there, we only know the true one. Right now, we don't. All right, over to Staplet. Over to Staplet. Okay, got all my favorite toys open. Staplet is the way to go. All right, this is second one from the bottom on the data analysis. 2 quantitative variables. Okay. Number of rail cars, yay. And response, fuel consumption, yay. All right. So now I will input the data. There's the grab the bottom one. Fuel consumption and the number of rail cars works very much like they've all been working. And here we go. Begin analysis. Yay! Pretty scatter plot. Completely labeled. Okay? Press that button. Correlation. Yay! Press that button. Okay? There's the equation of the least squares regression line. That number is a little bit different. I must have typed in a number wrong. Okay? There is the equation, the S. That's the S. That's your residual sum. That's your standard error of the residuals. R squared. So you got the R squared, S, and the full equation. They even put the Y hat there. Even giving you the option, look at this. I'm going to show you this. You can calculate a quadratic. Okay? And compare the R squares. Do they give you the, oh yeah, they do. They do, they did it. Do you see the little arch there? There's a little arch there. Yeah, that's the quadratic fit. Yeah, actually there's a quadratic fit and I just did that. I don't press that button often enough, but now, oh, it's even better. Let's see, calculate other regression models, perform an inference. Okay. Oh my gosh. Yeah. It does everything for you. I don't know if you can see this. A t interval for a slope, that's what we did. A t-test for a slope, that's what we did. Oh my gosh, a prediction interval for value of a response variable. Yes, it will do that. Right, so So you can check your work with that, right? Explanatory variable 40. Okay, level of confidence, boom, there it is. Right there. The other one is a confidence interval for mean slope, so I just did them in the other order there. Yeah, and then you just put in your explanatory variable, it does everything for you. Oh. Which is, yeah, really, the residual plot. Yeah, it's right there, right there. There's a residual plot. There's even a dot plot of the residuals. Yeah, everything's on here. It's great, so definitely wanted to share that with you. And that is it. Now the lead-off question is about regression. I don't ask everything, of course. I say, use software to generate, it's a small data set. It's a small data set. I didn't put you fuss with a large data set. Although this is easy. Use software to generate the equation for least squares regression line and accompany summary statistics. Just, let me see a copy of that output. Write the regression equation using the appropriate format. Identify and interpret the slope. Okay. Using the model. Okay. So this is predicting. This is for elderly people and who cannot stand. Trying to predict their height from their knee height. And it's actually used. How tall would you expect an elderly man to be if his knee height was 20 inches? Calculate and interpret the coefficient of determination. And you, to be clear, you don't have to hand calculate it. Now, get the numbers from here. But do show the calculations for E and F, and then you can check your work. I'm asking for the slope, complex interval with the slope, and the prediction interval. I did not ask for the mean response one. Yeah. So anyway, it's kind of short, but at least you have something start to finish. A really thorough treatment of regression. Everything that an undergrad course would get, and maybe a little more.
Yeah.
They generally don't do the prediction interval stuff. Okay, gang, I'll be around next Tuesday. The last day of classes are Tuesday. I've got that other class here. Everybody wants to get together.
What time are your? What time is the class? What time are your
Same as
hours?
ours, actually. Yep.
Oh.
Yep. 6 till whenever. And, I'm gonna do some simulation methods with that. Boy. So we wish you could see it. I mean, you're welcome to stop in. It's actually, it's over there, yeah.
Oh.
Yeah. It's really cool. I mean, yeah, I'm just playing out of time, but you mind a quick story? You know about the draft lottery of 1969, the military draft lottery? You know about this? You guys are, I'm too young for it. Okay. Imagine how this would go over today. You turned 18 in 1970. It was the time of the Vietnam War. It was a military draft. Men, you would give your name to the selective service, and then, okay, on an evening, a televised special, they pulled these little capsules out of a big bin with birthdays. The first birthday, I think, was September 18th, I think. And they did it for all 365. September 18th, your draft number 1. You're going to Vietnam. You're going to Vietnam. Yikes. Yikes. Well, it's a really cool simulation example of how that draft lottery was biased. Biased. It's biased against people who had a later birthday. It was biased towards people who had an earlier birthday. In other words, if you had a later birthday, you had a higher probability of getting a lower draft number and henceforth going to Vietnam. If your birthday was earlier in the year, a lower probability of getting a lower draft number. So it wasn't fair. Anybody know about this? Anybody ever heard about this? The reason is silly and stupid.
Yeah, what was their logic? Yeah, did they? Sure, they knew that.
It's silly. Let me see. I'd say great. If you need to go, that's fine. Let me see if I can find something on just very quickly. It's on YouTube. Okay, and you can see the explanation. Draft lottery, 1969. Boom, there it is. Oh, please tell me we can have sound. 60 minutes, they're talking about the draft lottery. So there they are. Yep, there they go. They're picking the capsules out of the bin.
Oh, that's craziness.
Yeah, picking the capsules out of the bin, opening a capsule, number 1. Watch their number. There's some clips from Vietnam right there. Okay. Yeah, I happily was too young. 1969, I was 12. Okay, here's the little capsules. Take a little birthday. All right. The explanation is. All right. Here's what happened. So stupid.
Oh, really?
So all the little capsules were in little boxes. January, February, March, April, May. And what they did, they put all the
They
Januaries,
just dropped it, yeah, in order.
Februaries, March, April, May, blah, 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 blah. All of the later birthdays were on the top. Oh, maybe they went in and mixed them a little bit, you know. Yeah, September 14th, there it was, September 14th. And you can even see it if you make a plot of the average draft number versus month, January, February, March, April, May, June, July, August, September, October, November, December. There's a little variation, but overall it's like that. The median draft number, where it should be, of course, like that. Yeah. So anyway, yeah, pull it up. Military draft lottery, 1869, and what we do is we use a simulation method. Using a simulation method, we actually create the draft lottery. We recreate it thousands and thousands and thousands of times. We look at the correlation between the birthday, okay, 1, 2, 3, 4, you know, were you born on the 1st, 2nd, 3rd, 4th, 5th, 6th, you know, the 366th day of the year, versus the draft number, okay? The correlation should be close to 0. It is not. It is statistically significantly negative, okay? And we do that by a simulation, where we use technology just to recreate the draft lottery thousands of times in a fair draft lottery, and look at the results, and then look at their results. Okay. So anyway, it's really, really interesting. I remember the first time I ever saw that. You have got to be kidding. No. Were they just ignorant of stats back then? No, statisticians jumped all over that one. The government said, hey, what's done is done. I'm not doing it again. They did fix it the next year. They had it the next year. Right. This is stupid too, sorry, but so as the story goes, I can't find any clips of it. Now they said they had 2 rotating drums. 2 drums that rotated. One had your birth date and the other had a draft number. and they would stop the drums, and they would pick one from here and one from here. All right, that's overkill. All you have to do is randomize one of them. Jeez. And then there's a story of one of the drums broke down anyway, so.
We're really trying to cover their bases there to say they're not being biased.
That's right. That's right. Well, yeah, you might want to look at that other book, because I'll tell you another example that we did. We did logistic regression, which we look at a data set on the Challenger explosion. And why the Challenger? Okay, again, you're too young for that. 1980s, the space shuttle Challenger, first teacher in space, blew up with like every kid in America watching that thing at school. Ugh, that's terrible.
What was, did they not account for something
It's an
contracting?
O-ring failure.
O-ring,
It's an
yep.
O-ring failure because the launch was done on a very, very unusually cold morning
Yeah.
in Florida. And NASA released that data, and now it's a standard exercise in logistic regression, calculating the probability of an O-ring failure given the temperature. That's what that
Yeah.
process is for the one. All right, guys, stay in touch, definitely, as will I.
Thank you.
There's multiple limits of expression in the class, which I know it's not that much, it's just raising the